Today we're going to look at the double angle formulae. These are a special version of the addition formulae that we looked at last week for finding compound angles of sine, cos and tan. So I've written down those formulae. Remember, these are in your formula book, so you don't need to remember these. We've got one for sine, one for cos and one for tan, and it's sine of the angle A plus B. So if we've got the addition of two angles and we want to find sine of that. Now we can use this to work out the value of sine of A plus A just by replacing all of the B's with A's in this formula. And obviously sine of A plus A is sine of 2A. A plus A is 2A. So this is why they're called the double angle formulae, because they're for the double of an angle. And what we get is sine A cos A plus cos A sine A. Now obviously these two terms are identical, just written with the product the other way round. So we can write this as 2 lots of sine A cos A. And that's our first double angle formula. This is not given to us in the formula book because we can work it out in 5 seconds flat. So sine of 2A is 2 sine A cos A. We can do the same for cos. So if I replace B with another A throughout the formula, it now gives me cos of A plus A, so cos of 2A, and that equals cos A times cos A, which can be written as cos A all squared. Remember, we put the squared on the cos here, so cos squared A. And then we've got a subtraction of sine A times sine A, so that's sine A all squared, which again we write with the squared on the trig function, so as sine squared A. Now that is how I remember cos 2A, as cos squared A minus sine squared A, but that's not always the most useful form of this formula. Remember that cos squared plus sine squared makes 1, and I can use that fact to manipulate this formula so that it's only in terms of cos or only in terms of sine. So I can replace cos squared A with 1 minus sine squared A, and that gives me 1 minus sine squared A minus sine squared A, or if I want to simplify that, that's 1 minus 2 sine squared A. So that's another form of this compound angle formula. Cos 2A equals 1 minus 2 sine squared A. Or I can replace the sine squared A with 1 minus cos squared A. So I can write it as cos squared A minus 1 minus cos squared A. Well, taking away 1 minus cos squared A is the same as taking away 1 and adding cos squared A. So this can be written as 2 lots of cos squared A minus 1. So that's the third form of this double angle formula. Cos 2A equals 2 cos squared A minus 1. Again, this isn't given to you in the formula book. None of those formulae are in the formula book, but you can derive it. So I always go from here to cos 2A equals cos squared A minus sine squared A, and then adapt it using the identity that cos squared plus sine squared equals 1. Right, finally we've got the tan formula. So if I want tan of the double angle, I want tan of A plus A, so I'm going to replace all the B's with A. So tan of A plus A is tan of my double angle, tan of 2A, and that gives me tan A plus tan A, or 2 tan A, over 1 minus tan A times tan A, which is tan A all squared, which we write as tan squared A. So that's our double angle formula for tan. So there's only one version for sine and tan, but there's those 3 versions for cos. And these are all written at the top of the notes sheet for this lesson. So it's just done by swapping your B's for A's in the addition formulae, and there they all are written there. So let's have a look at some examples of the sorts of questions that you might get asked. We might get asked to simplify some expressions, so something like 2 cos squared 30 minus 1, and this fits into this form here, 2 cos squared of an angle take away 1. So that is going to equal cos of 2 lots of the angle. So cos of 2 lots of 30, which is cos of 60. Just asks us to simplify it in this question, but it might ask us for the exact value of it, which we can then work out using the exact values that we know to be a half. For part B, we've got 2 sine 45 cos 45. So that is of this form here, using the sine double angle formula, where our angle has been replaced with 45 degrees. So it's going to be sine of 2 lots of 45. So sine of 90 degrees, which if we wanted a value, we would know to be 1. For part C, again we're looking at the cos formula, and it's this one here, 1 minus 2 sine squared a. So that's going to be equal to cos of 2a, where a is 5x. So cos of 2 lots of 5x, cos of 10x, if we simplify it. And then for part D, it's obviously the tan formula, where the angle A has been substituted for 3x, so that's tan of 2 lots of 3x, so tan of 6x. So that's all just using those formulae and just substituting some angles in. For question 2, we're asked to solve an equation. We've got cos of 2x plus 3 sine x equals 2, and we can't solve an equation like this where we've got different numbers of angles in our different trig functions. So we're going to replace cos of 2x with one of these expressions where we've only got single angles. Now it makes sense, because the rest of our formula involves sine x, for us to replace cos 2x with something involving sine. So we're going to replace it with 1 minus 2 sine squared x. And this gives us a quadratic equation involving sine. We've got sine squared, we've got plain sine, and then we've got a constant as well. So if I rearrange this to make it equal 0, I've got 2 sine squared x minus 3 sine x plus 1 equals 0. And I can solve this by factorising or using my calculator. Either way, I get the value of sine x to be a half or to be 1. I know that between 0 and 360, I get a sine value of 1 at 90 degrees and only 90 degrees. And I know that I get a sine value of a half at 30 degrees. So that's one of the values that we should know. I will also get it 30 degrees back from 180, so at 150 degrees. So my values of x are 30 degrees, 90 degrees and 150 degrees if I write them neatly in ascending order. So for question 3, we're using tan. So we've got tan x times tan 2x equals 1. So let's replace that tan 2x with single angles using this formula here. So it's going to be tan x times 2 tan x over 1 minus tan squared x equals 1. So that can be written as 2 tan squared x over 1 minus tan squared x equals 1. And then if I multiply through by my denominator, 2 tan squared x equals 1 minus tan squared x. So 3 tan squared x equals 1. So tan squared x is a third. So square rooting both sides gives me tan x is 1 over root 3. So square rooting the 1 gives me 1, square rooting the root 3 gives me root 3. Don't forget though, if we're solving an equation involving squared, we need to consider the negative root as well. So we could have tan x is minus 1 over root 3 as well. Now we're working in radians here, so it's a value we should know. 1 over root 3 is the same as root 3 over 3, which we know is tan of 30 degrees, but we need to be working in radians, so we need to be working with pi over 6. Or for minus 1 over root 3, your angle will be minus pi over 6. Remember, tan is an odd function. It's got that rotational symmetry about the origin. So if we've got one value for a positive angle, we'll have the negative value for the negative angle. And we're interested in between 0 and 2 pi. Remember that the tan graph repeats itself every 180 degrees. So we just need to add or take away multiples of 180 degrees or multiples of pi from these angles. To get between 0 and 2 pi, I just need to add pi. So another possible value is 7 pi over 6. Obviously this value is not in the range, but adding pi gives me 5 pi over 6, which is in the range, and adding pi again gives me 11 pi over 6, which is also in the range. So our final answers are pi over 6, 5 pi over 6, 7 pi over 6 and 11 pi over 6 when they're written in ascending order. Right, question 4 is proving an identity. Now make sure you do this really carefully. I had to write a lot of targets on your work on identities, that you must only work with one side of the identity and ignore the other side completely, but hope that you get to that as your final answer. So we normally start with the most complicated looking side of the identity. So that's obviously the left hand side here. So I'm going to write down that left hand side so everyone knows exactly what I'm starting with. And then I'm going to use identities to simplify this. It's got double angles in it, so let's use our double angle formulae to write cos of 2x as cos squared x minus sine squared x. And sine 2x as 2 sine x cos x. Don't forget to put brackets around your cos squared x minus sine squared x. So if I expand out that bracket, that's 1 minus cos squared x plus sine squared x over 2 sine x cos x. 1 minus cos squared x is the same as sine squared x. So this gives me 2 sine squared x over 2 sine x cos x when I add the sine squareds together. And this fraction will simplify. I can divide top and bottom by 2, and I can divide top and bottom by sine to get sine x over cos x, which will simplify to tan x. And this is where I look up at my original identity and see that I've got to my final answer of tan x. So at no point did I use that to help me with my working. I just check it at the end and see that I have simplified it in the way that they wanted. Right, question 5 is asking us for a triple angle formula for cos 3x. Now cos 3x could be written as cos of 2x plus x. So I've written it as a compound angle. And I know that cos of 2x plus x, using the formula from my formula book, is cos 2x times cos of x minus sine 2x times sine of x. So just using that formula from the formula book that says cos of a plus b is cos a cos b minus sine a sine b. Now I've split it up, so I've got single angles, great, and double angles, which I can simplify using my double angle formulae. So cos of 2x is cos squared x minus sine squared x. And sine 2x is 2 sine x cos x. So this is a triple angle formula, but it only wants it in terms of cos x. So everywhere that I have a sine x, I need to replace it with something in terms of cos x. So where I see sine squared x here, I'm going to replace it with 1 minus cos squared x. And here I've got a sine x times a sine x, so that's a sine squared x, so that can also be replaced with 1 minus cos squared x. And I've done exactly what I needed to do. This is actually a triple angle formula in terms of cos x, but let's make it look a little bit neater. So I'm just expanding this bracket here, so taking away 1 and taking away minus cos squared x gives me minus 1 plus cos squared x. And expanding this bracket here gives me minus 2 cos x plus 2 cos cubed x. So I've just got one bracket left to expand here. I get cos cubed x minus cos x plus cos cubed x. So now if I just collect like terms, I've got 1, 2, 4 cos cubed x minus 3 cos x. So that's your triple angle formula. You do not need to know that, but you might get asked a question like this in an exam where you've got to derive it, or you might be asked to derive it in terms of sine. Okay, question 6. We know that sine A is 8 over 17, and we want to find the exact values of sine 2A, cos 2A and cos 4A. Now in all my double angle formulas, I need sine and cos of the angle. So if I know that sine A is 8 over 17, sine is the opposite over the hypotenuse. So in a right angle triangle with an angle A, the ratio of the opposite the hypotenuse is 8 to 17. So I can find my adjacent using Pythagoras' theorem. So using my calculator, my adjacent is the square root of 225, which is 15. So that will tell me that cos, which is the adjacent over the hypotenuse, is 15 over 17. Remember, you need to check the sign of that. Is it positive or negative? Since A is acute, that's between 0 and 90, and we know that cos, using the cos graph, is positive between 0 and 90. We're going to be using positive 15 over 17. Remember, you can also use the cast rule to do that. So using the cast rule, you can see that all of the trig functions are positive between 0 and 90. So that also tells us that cos will be positive here. So let's start by doing sine 2A, and that is going to be 2 sine A cos A from our double angle formula. So that's 2 lots of 8 over 17 times 15 over 17, which is not going to be a particularly nice number. $240 over 289. And then cos of 2a is cos squared a minus sine squared a. So that's 15 over 17 squared minus 8 over 17 squared. Which gives us 161 over 289. And finally we want cos of 4a. Now cos of 4a is the double angle of 2a. So we want cos of 2 lots of 2a. So using my double angle formula, this is cos squared of 2a minus sine squared of 2a. So cos of 2a was 161 over 289. So I need to be doing that squared. And sine of 2a was 240 over 289. So I need to be subtracting the square of that. I think we can be very grateful we've got a calculator here. We get minus 0.133 to 3 significant figures. I think we could do with the exact value it asks for here, so I may have to type it into my calculator slightly differently. So my numerator will be 161 squared minus 240 squared, so minus 31679, and my denominator will be 289 squared. Isn't a particularly pleasant fraction, but at least we have it accurate. So that's the work on the double angle formula. You just need to have a go at the worksheet now.